Okay. We're going to go straight into the notes since we didn't have homework. And we're going to continue this continuity that we were talking about last class. So I'll continue the continuity that we were talking about last class and seeing some other applications. Now I switched the order of the slides. I'm doing this before the slide that was next, so I just moved this one slide forward because I found we need these definitions to help with those problems that we're going to do next with the 5A and B. All right, so there's a few things that we need to know about continuity of functions. So there's certain equations, certain functions that are continuous, that we know they're continuous, and if we know that this equation is that type of function, we know that they are continuous, and that will help us. And we know that where they are not continuous, and that's what we're kind of look at here. So a function is continuous on an interval. On an interval, left out my R, interval, if and only if it is continuous at every point on that interval. Okay, that makes sense. Now, these are some functions that are continuous everywhere, or everywhere that's defined in this domain. So one is a polynomial function. Polynomial function is one that is continuous at every point of its domain. So what does a polynomial function look like? When I say polynomial, what are you thinking of? How?
X squared and X.
Yeah, so there any equation that you have like f of x is equal to, here's some examples, x squared plus 4x minus 5. That's a polynomial. G of x is equal to 4x minus 3. It's actually a linear function, but linear is inside polynomials. So it's anything where the x is raised to a power that is a positive integer. That'll give us polynomials. And we can have as many of those terms we want. And if you're looking at x squared plus 4x minus 5, what's the domain of that polynomial? What possible x values fit? What was that? Any. So this domain here is all real numbers. What about the linear function 4x minus 3? What's this domain? Huh? Everything. It's infinity as well. In fact, all polynomials are defined everywhere. That's powerful. But it's one of those functions continuous everywhere in its domain, and polynomial functions is always defined. Unless, you have a piecewise function, we limit the piece that we're looking at. Okay? So that's going to help us. So we know it's always continuous, everywhere it's defined, and it's defined everywhere. So polynomial functions are defined everywhere. That helps us. All right, a absolute value function is continuous over every real number. So you can think of that. So, you think about that. One absolute value, the very simplest absolute values, f of x is equal to the absolute value of x. So think about that graph of that function. That's f of x equals absolute value of x. So that's that function. So what possible x values work there? Any of them, any real number. So the domain here is also all real numbers. So that's nice. Our problem is in calculus we don't just set with a simple absolute value. We're going to have absolute values mixed with other functions. So it becomes a little bit more tricky. But this by itself, that's good to know. Okay. Rational functions. Rational functions are continuous at every point of their domain. All right, so let's talk about what's a rational function. That's radical. That's okay. That's a radical function. So it can be made into a fraction. Rational functions, here's an example of a rational function. It's something like 1 over x plus 3. Or x minus 3 over let's say those are rational functions, meaning with the fraction, with the x in the denominator. Give us a rational function. So rational functions are continuous at every point of their domain. So let's talk about finding the domain of rational functions. What is the domain of f of x here? How do we figure out its domain? What x's work and what x's don't work? What do we know we can't do? We can't have a zero on the bottom. So to figure out what doesn't work in this, you always set your denominator not equal to 0. So I know x cannot equal negative 3. So my domain for this problem, over here. So domain for f of x would be everywhere but negative 3. So that would be from negative infinity to negative 3 union negative 3 to infinity. Graphically, what's happening at x equals negative 3? It's undefined. Why is it? What's happening on the graph that makes it undefined? It's a point of discontinuity, yes. So it's not in its domain, so it's going to be a point of discontinuity. What kind of discontinuity is it? I didn't hear those. Yeah. What's happening at that point? When the x is negative 3, what's happening on our graph? Okay, get your calculators out. Graph 1 divided by x plus 3. Let's see what's happening. Remember all this college algebra stuff. It's an asymptote. It's a vertical asymptote to be exact, right? So these rational functions, they have a point of discontinuity at the zeros of the denominator. Because I set the bottom equal to 0, so at the zeros of the denominator, where the graph of the function has a vertical asymptote. What would be the equation of this vertical asymptote in this problem? The equation of that asymptote in the one you just graphed. Now remember, for vertical asymptotes and horizontal asymptotes, is equal to x equals the number or y equals the number. So in this one, if it's vertical, all the x's are the same. So our equation would be x equals negative 3. So that'd be equation of our vertical asymptote there. Okay, let's look at g of x now. What is the domain of g of x? How would I figure that out? That's the bottom. So you have to figure out the zeros at the bottom. So we're going to have to factor that. Does it factor? If so, how? X plus 2, x plus 1. Yes, that works out. So therefore, x cannot be what values? All right, so our domain for g of x would be what in interval notation? What did I write that? Perfect. Negative infinity to negative 2, union negative 2 to negative 1, union negative 1 to infinity. So I know that function g of x is going to be continuous everywhere except negative 2 and at negative 1. Now, because the graph, what's happening to the graph at negative 2 and negative 1? It's a vertical asymptote. So what kind of discontinuity is happening at vertical asymptotes? Infinite. So because there's a vertical asymptote there, I know I have infinite discontinuity at those 2 points. Now, you should get a fraction. If I change g of x slightly to this equation, make it h of x. We'll make it x plus 2 over the same denominator. What's the domain? What's our asymptotes? And the type of discontinuity. That occurs. All right, so to find the domain, I do the same thing. Set the bottom equal to 0. We've already figured that out. So that domain is the same as what we did already. And then we worked that already to get x cannot equal negative 2 or negative 1. So my domain is still there. But when I rewrite h of x in factored form, what happens? X plus 2 cancels out, right? And I get 1 over x plus 1. And notice, I got my domain from the original before I canceled out. Because by the original function, it doesn't exist at that negative 2. But what's happening at negative 2 now? Is it an asymptote still or not? What happens when you cancel out? Try sketching this one and see. How does the graph change? You can even sketch g of x and h of x to see how it changes. What happens? Huh? Try going back to, when something like that, go to zoom, you go down to standard. You have to go to the sixth one. How you get mixed up like that. Yeah, you might want to clear off those other pictures. Yeah. So what's the difference between g of x and h of x in this graph? Oh, there's no longer vertical asymptote at negative 1. But try tracing or try to figure out what's the function value at negative. I'm sorry, at negative 2. There's no vertical asymptote at negative 2. But try tracing that. What's happening when you get to negative 2? It says error. It says error. So when you cancel a point out like that, that means you have a hole in the graph. At negative 2. You get an error there. So it's not in the domain, so it can't be there. So that's an open circle. The function can't do that. The calculator can't draw open circles. And so it just shows you error when you do the trace. So my asymptote is only at x equals negative 1. But I have 2 types of discontinuity. At x equals negative 1, what's my discontinuity? Okay, that's the asymptote. So that's infinite discontinuity. at the hole in the graph, what type is that? Point or removable. So we have point discontinuity x equals -2. But everywhere else, because everywhere else is in the domain, it's fine. So it's only those points that's not in the domain. I need more room on this. I should give myself more room. I gotta remember all this. In fact, we can do pretty much the same thing for all exponential functions or logarithm functions and all trigonometric functions. And rational functions. Those are those square roots and cube roots. All exponential functions, all linear functions, all trigonometric functions, and all rational functions will be continuous everywhere that they are defined. So obviously, our first step in a lot of these problems is going to figure out the domain of the function given. We have to go back to figure out our domain of the function given. And so we know where it's continuous and where it might not be continuous, where it's discontinuous at. So that's going to be our first steps on all these. It's figuring out those domains. We have to learn to recognize functions, types of functions, so we can see what works. Okay, so we got to use this to work on these other types of questions. I got that down. All right, so we're going to find values of a and b for which the function is continuous. So we're going to make these continuous. Okay, it's a piecewise function. So if I look at the top piece, what kind of function is that? That's a linear function. So it is defined where? But defined is another way of saying the domain. What's the domain? Everywhere. So it's defined everywhere. Which means, like this, which means we'll just write function. So it is defined everywhere. Therefore, the domain is -infinity to the 1. Just because that piece is only defined up to 1. Now, it says or equals to 1, but I'm not going to include 1 yet because this is a piecewise function, and it might be defined here at 1, but this piece might be down, so I might have jump discontinuity going on. So I can't include 1 as being sure it's in my domain that's in my continuous yet, because the piece is right up there. What about ax squared? What kind of function is that? Ax squared is a polynomial. So what do we know about its continuity? So it is continuous everywhere in its domain. And we know its domain is -infinity to infinity, but in this case on the piecewise it's from 1 to infinity. So I figured out that this polynomial grid, just looking at those rules about which type of function it is, I've been able to now figure out that the only possible problem I could have is at 1, right? Everywhere else this is going to be continuous. So the only point that I might not be continuous is at 1. That's got dropped out. Okay? So anywhere it might not be continuous is at the 1. And so since it might not be continuous at 1, I need to choose an a value in this case so that it is continuous. And the only way it can be continuous is if it meets those 3 requirements of continuity we talked about last class. What was those 3 requirements? F of x exists, so f of a exists. The limit exists. The limit equals the function value. So we're going to use those three now to talk about at x equals 1. So let's see if f, try that again. Let's see if f of 1 exists. Because 1 is our problem that we need to fix. So which equation should I plug 1 into, top or bottom? The top one. So I plug in place of x 1. 7 minus 2 is 5. It exists. Right? So now I need to make a so that my limit exists as well. In a piecewise function, how do I know the limit exists? When the limit from the left equals to the limit of the right. So let's talk about the limit as x approaches 1 for the left. For this to be continuous, that must equal the limit as x approaches 1 from the right. That's going to give us that's going to make the limit exist. And we want to make this continuous. So, the limit from the left, which equation should I use? Top or bottom? Top. Okay, so that's 7x minus 2. And for the limit from the right, which equation? The bottom. So that's going to be ax squared. And let's do direct substitution, evaluate those limits. So that gives me 7 times 1 minus 2, which is 5. And this gives us a times 1 squared, which is a. So for this limit to exist, a must be 5. That statement must be true. Left limit must equal the right limit. Now I just check and make sure it meets the third requirement. So the limit as x approaches 1 of f of x must be, if a equals 5, we can plug in place of a 5. 5 times 1 squared gives us 5. And this one gives us 5, so it's equal to 5. That works. Function value is 5. They are equal to each other. So the only a that makes this piecewise function continuous is if a was 5. That's the only polynomial that would work there. You try this one. Same kind of concept, this time you just have 2 a's. But I say such that this function is continuous everywhere. Hey Eric, are you having internet problems today?
I accidentally missed 2 classes this morning because of internet problems. It just rained here.
Oh, okay. I know what that's like. All right, let's check and make sure everything's okay. So we're working on this, trying to prove that this is we're finding an a value that makes this f of x continuous. And Eric, if you missed too much today because of the internet, just send me an email and I'll try to give you the video of this in case you missed some important parts.
Thank you. I might have to do that.
Okay. so let's see how you did. All right, what kind of function is ax squared? Polynomial. Oh, let's pause. I would eventually figure it out. Ax squared, and what kind of function is 2x plus a? That's linear, which is another form of polynomials. And 2x plus a are polynomial functions. They are continuous everywhere. Everywhere defined. Therefore, x equals 2 is the only possible point of discontinuity. Another way you can put it together. So I kind of put it together in one minute this time. Okay. So since that's the only possible point of discontinuity, that's the way it's going to get us from. So now we got to figure out, we got to make it continuous at x equals 2. That's what I'm looking at, continuity at x equals 2. So I need to figure out my function value at 2. So what one would I plug in to get my function value at 2? Top equation, so it's going to be a, place x with 2. Didn't get rid of the a, but that's okay. So it's going to be 4a. The limit needs to exist, so that means a limit from the left. Limit as x approaches a from the left, which would be top equation or bottom equation? Top must equal the limit as x approaches a from the right, which is the bottom equation. Alright, so direct substitution in. Place every x with 2. Place every x with 2. So I get 4a is equal to 4 plus a. So I just solve this equation for a. What would you do to solve? Not yet. Get a's together first. So subtract the a, that gives us 3a. And then divide by 3. So a should be equal to 3/4. I'm just going to check and make sure that works out. So if I replace a with 3/4, that gives me 4 times 3/4, which is 12/4, which is 3, right? Okay. 4/3. Thank you. I wrote that totally backwards. No one else was saying anything. Thank you. 4 divided by 3. I flipped that over. Good call. Good catch. All right. So that's 16/3. Now let's check each limit. 4 times 4/3. That's 16/3. 4 plus 4/3. Oh, that one's a little bit harder for me to do in my head. Common denominator becomes 12 over 3 plus 4 over 3. That's also 16/3. So yeah, it meets all the requirements. You either show that work of checking or just check it in your head. I usually just check it in my head. Make sure it might work. That way you can always check and make sure your answer is correct. All right, let's do one that's a little bit harder. This is going to require us to use the systems of equations to solve it. So try this one. Last one we're going to do together. Or last one I'm going to have you try. So find a and b this time, so that this function is continuous everywhere. It is continuous. F of x is continuous. so let's start with saying since x plus 1, ax plus b, and 3x are all linear functions, then I know they're continuous or where they're defined, therefore this function is continuous everywhere except where this break up, which is at x equals 1 and at x equals 2. So I have to work through and figure out for x equals 1, gotta find an a and a b so that it is continuous. And x equals 2, I gotta find an a and b so it is continuous. So we'll start with x equals 1. Alright, so f of 1 must exist, the limit must exist, and the limit must equal the function value. Those are our three requirements. So f of 1, according to this, which equation should I use? Which one? The middle one. That's a, x is going to be 1 plus b. That just becomes a plus b. That's my f of x value, f of 1 value. A plus b. Then for the limit of piecewise function, that means the limit as x approaches 1 to the left. And which equation would that be? X plus 1, the top equation, must equal the limit as x approaches 1 from the bottom, which would be x approaches 1 from the right, which would be this the middle equation, which is ax plus b. So these are basic ones. I just do direct substitution. Like every x was 1. And I get 2 is equal to a plus b. Oh no, I'm stuck. 2 is equal to a plus b, and f of x equals a plus b. So that doesn't help me much yet. So I move to my other requirement. And now let's look at x equals 2. Alright, so let's figure out what f of 2 is. So which equation should I use for f of 2? The bottom one, the 3x one. So f of 2, therefore, is going to equal 3 times 2, or 3 times x, which gives us 6. And then the limit must exist. So we're going to have to do the limit as x goes to 2 from the left. Which equation is that? The middle one. That's ax plus b must equal the limit as x goes to 2 from the right is the bottom equation, 3x. So therefore, using direct substitution, I get a times 2 plus b must equal 3 times 2. So 2a plus b must equal 6. So I got 2 bits of data here. So let's put that together. I now have a piecewise function of 2a plus b equals 6 and a plus b equals 2. I need to solve this piecewise function, this system of equations. So we have the elimination method, the substitution method, matrices. We've learned all kinds of methods to follow down first. How would you want me to solve this one? Elimination is pretty much set up right now to take top function minus the bottom function. So I can just set that up. So 2a minus a gives me an a. B minus b cancels the b out. 6 minus 2 gives me 4. I found a. Now a is 4. How do I find b? Plug it into one of those equations. I don't care which one. So I'm going to get a plus b equals 2. So 4 plus b must be 2. Therefore, b must be negative 2. Double check and make sure that all works out in our pieces that we got up here. A plus b, so 4 plus a negative 2 is 2, must equal a plus b. That's 2. So 2 equals 2. Yay, that one worked out. And then for the 2 one, we had 6, so 2a plus b must equal 6. 2 times a is 8. 8 plus a negative 2 is 6. There we go. It works out. So sometimes you also have to use piecewise function systems. So don't you love calculus? You have to use everything on the class. It shows up when you least expect it. Everything just keeps coming up. Questions over this one? For finding the A and B value so that you have continuity. Okay, I'm gonna do this type is similar, but it's just slightly asked a different question. So here we're going to kind of put this together. We're going to state whether or not the following function is continuous. If there is any point of discontinuity, we're going to state where the discontinuity occurs. We're going to identify the type of discontinuity. And if the type of discontinuity is infinite discontinuity, we're also going to give the equation of the asymptote discontinuity. So those are things that we're going to look at. All right, so let's look at f of x here. What kind of function is that? No? Rational. Okay, so what do we know about continuity of rational functions? Okay, so rational functions, this is a rational function, so we know rational function is continuous everywhere except for the denominator equals 0. So I know f of x is a rational function. It is continuous everywhere except where 2x squared minus x minus 1 equals 0. All right, so let's figure out where that is at. 2x squared minus x minus 1 equals 0. So we need to try to solve that. So that's a factor. It does. We can figure it out. 2x plus 1, x minus 1. Alright, so 2x plus 1 equals 0. So x is equal to negative 1/2. X minus 1 equals 0. X is equal to 1. What do I do with that? What does that come? And so what about the continuity of those 2 points? Okay, so f of x has infinite discontinuity at x equals negative 1/2 and x equals 1. Vertical, and then they also said find the, if it's infinite discontinuity, find the equation of the asymptote. So vertical asymptote equations are what? Like the equation of those two vertical asymptotes. They're right there. Yeah, x equals negative 1/2. And x equals 1. Yes, it's already there. Not too hard. Okay. See if you're still copying. Try this one. F of x is equal to x divided by x squared plus 1. So we would usually try to do it be everywhere where it's defined. So this is a rational function, so it's continuous everywhere it's defined. Alright, so let's figure out where it's defined at. So x squared plus 1, we set that equal to 0. Can't factor, so let's just subtract that. that? That's I. Okay? Do we graph complex numbers? I. No, we're looking at all the real numbers. We're looking at the real. So this is continuous everywhere it's defined, and it's defined from negative infinity to infinity. This is a continuous function. No points of discontinuity. Bottom will never equal 0. The continuous function. And we're going to do a piecewise, then actually value, and we'll move on to the next topic. And now I want you to try a piecewise here. Same directions. Figure out any point of discontinuity for f of x, which is our activity. If there are any points of discontinuity, if you're going to find a type of discontinuity here, if there's infinite discontinuity, identify the asymptote. Okay, what type of function is the top? Rational, so it's going to be continuous everywhere. It's defined on possible point of discontinuity would be at x equals 3. We'll set that up. But notice if I look at that top equation. If I simplify that, what can I do? So, what do you mean by take out the negative? I can cancel out the x minus 3, right? Alt factors to that. So I know if I have a discontinuity point, it's not going to be infinite. What type of possibility could I have there? Pivot point, or because it's a piecewise, it could jump. So I could have jump discontinuity there. So right now, I know I don't have infinite discontinuity. Still have a possibility. I don't know if I have discontinuity at 3 yet or not, but it's a possibility. What kind of function is 8? Constant. We call it constant. When it's just this is that horizontal line. But because it's only defined at 3 is actually a point in this case. So that is definitely continuous there at that point where it's defined. And so I need to figure out if I have jump discontinuity or removable discontinuity. How can I find that out? I need to look at, let's look at our 3 possibilities for our 3 that we need for continuity. So let's figure out f at 3. So which equation at 3 do I plug it into? Bottom, so that's just 8. Okay, then the limit as x approaches 3. Now, what equation is it from the left? What equation from the right? The top. So I can just do it one way. So let's do that one. I get, when I do direct substitution, what do I end up with? 0, 0. That's how I knew I needed to do this. Factoring. Which we've already figured out. It's just x plus 3. And so when I plug that in, I get 6. So is my limit as x approaches 3 of f of x equal to my function value? So we have discontinuity. What type? Jump. So I went from a value, from the function value is at 8. No, wait, function value is at 8. And our limit from left and right is approaching 6. So limit is approaching 6, and function value is 8. So it is not jump. It'll be point. Because it's just because it's a single point and not an equation. point discontinuity.
Could you not solve it by like doing direct substitution?
What do you mean take out the negative?
Like, because I told us that we can like factor out if it's like something over something and you get zero, and like back up.
You can do fact, but you can't factor out of it. No. Yeah, you can't do that. You can only factor out that you want it to be still okay. Okay. Yes. We call it, which is not equal to our function value. Alright, last one of this type, because I want to make sure you have an example of each and every value. And then we need to get the intermediate value theorem. Got to get through it today. I'm not going to do the other piece-wise examples. Okay, so here, f of x is equal to x divided by the absolute value of x minus 3. Here, I can't say this is a certain kind of equation because it's a rational function and an absolute value together. So we don't really have a name for that. So I need to figure out how I can work this through continuity. And what do we know that we always have to do to see an absolute value in a problem? Piecewise. So break that up to a piecewise function. So that's going to be your first step. Rewrite f of x as a piecewise. And then it's going to be a lot like that piecewise we just did. Alright, so absolute value of x can be broken down to negative x when x is less than or equal to 0, and x when x is greater than 0. Agree with that? So that means f of x can now be rewritten as x over negative x minus 3, which replaces the absolute value of negative x when x is less than or equal to 0. And x over x minus 3 when x is greater than 0. I need to add another condition here. Let's look at that first rational function.
Greater than or equal to, or less than or equal to?
Yeah, you could have said less than, and here you could have said x is greater than or equal to. So the or equal to doesn't matter which one. You only put it on one. It doesn't matter which one you put it on. All right. I now have another condition here because now I know I have two rational functions. And this rational function is defined everywhere except when the bottom is equal to 0. So let's figure out where the bottom equals 0 for the top function. Where would that be? So negative x equals 3, so x equals negative 3. So this tells us that x cannot equal negative 3 for this equation. What's happening at negative 3? We have an asymptote. Okay, vertical asymptote. So what kind of discontinuity do I have at negative 3? Infinite. So I can go ahead and put that. So x equals negative 3. We have infinite discontinuity. What's the equation of the vertical asymptote there? Okay. Vertical asymptote, x equals negative 3. All right, now let's look at the bottom equation. It's a rational function, so it's defined everywhere except everywhere in its domain. So it's continuous everywhere where it's defined. So it is everywhere except for the bottom equals 0. So where does that happen? At x equals 3. So this cannot exist at x equals 3. So we have another infinite discontinuity at x equals 3. And we have another vertical asymptote at x equals 3. Alright? So now, where's another possible point of discontinuity? So we've covered the 3 and the negative 3. When we have division by 0. I got a piecewise function. So when can a piecewise function be discontinuous? Where the two pieces meet. So we got to figure out if it's continuous at 0, where the breakup of the two pieces are. So now we got to check at x equals 0. We got to prove it's continuous at x equals 0 by using our 3 proofs of continuity. So what's our function value at 0? So in this case, in mine, it'll be the top function. So that gives us 0 over negative 0 minus 3. What's that? 0 over negative 3, which is 0. For yours, at your bottom, 0 over 0 minus 3. 0 over negative 3 is still 0. That's the reason why it doesn't make a difference. Or which one you put it with. So f of x, so it's defined. We got an answer. Okay? So we fix that one. Now I got to compare the limit as x approaches 0 from the left, which will be my top equation, and compare that with my limit as x approaches it from the right. So as x approaches it from the left, what answer do we get? It's still 0. And the limit as x approaches to from the right is 0. So the limit from the left equals the limit from the right, so my limit is 0. So it meets that second requirement. Okay, and our limit equals 0, which is equal to our function value. So it is continuous at 0, so I only have 2 points of discontinuity. But you have to check that because at any places that piecewise function breaks up, there always be points of discontinuity, either removable or jump. You have to test those.
Function value?
Mm-hmm.
Like, how do you go to use the bottom? Or the negative one?
Wherever I had defined x equals 0. So, and like I said, if you did the bottom one, it's still going to be the same answer. Yeah, so wherever you had said x equals 0 on your piecewise. Okay, so I'm going to skip those two because we need to get to our first important theorem of calculus, the intermediate value theorem. Instead of writing that down every time, the abbreviation is IVT, much universally accepted. That's our first theorem. A function y equals f of x a function y equals f of x that is continuous, so that's our condition. So before I can use the intermediate value function, we first have to have a continuous function. That's what that means. On a closed interval, what does closed interval mean? That means you include the endpoints. Bracket, bracket. Okay, so a closed interval from A to B where the endpoints are included. So the function f of x that is continuous on a closed interval from A to B takes every value between f of this, or f of A, and f of the other endpoint B. That's the theorem. Now I'll have to explain what that means. That's our theorem that we'll be using. The intermediate value theorem says f of x, a function f equals y equals f of x is continuous on a closed interval from A to B, then for every function between f of A and f of B exists. Okay, so basically that's it's saying, think of it picture-wise. I'm always a practical person, so I think it's picture first. So let's say I have, here's my A, here's my B, so A and B is on my x-axis, so that's in our domain, so that's on my x value. And I have a function, say this function here. Notice that the requirement is it has to be continuous. So I can't have any points of discontinuity from A all the way to B. That has to be continuous. If that is continuous from A to B, we can conclude, this is the conclusion, I can pick any x value in here, in that interval, any x value I want in that interval, and I am guaranteed to find a y value that is between the y value of f of a and the y value of f of b. That's all it says. So if I pick any point here, any value here, my function value will be equal to or between f of a and f of b. That kind of makes sense, right? If you're continuous, the only way you're going to get from this point to this point is you're going to have to include all points. Now, I could have drawn A and B might look slightly different. I mean, you could do something like this. And so I have A here. That's my A. That's my F of A. Here's my B. Here's my F of B. So any point in here, there must exist at least one value that has the same y value. In this case, there's 1, 2, 3, 4, 5. But there's at least one. What we have for a continuous function. That's what the theorem states. So anytime we work with this theorem, anytime you want to use the intermediate value theorem, the first thing you have to prove is that the function is continuous. So that is the requirement to use this theorem. So before you can use the theorem, before you can say I've used the intermediate value theorem, we know this occurs, we first have to prove continuity. That's going to be our first step every time. Okay, so let's try some examples. So f of x, so function f of x on a closed interval from a to b are given. Show whether the conditions of the intermediate value theorem holds for the given value of k. If the condition holds, find a value c such that f of c equals k. So k is my y value there. That's what's telling me f of c equals k. K is y. If the theorem does not hold, give a reason. And regardless of if it holds or does not hold, we're going to make a sketch of this function and the line y equals k to illustrate that it works or doesn't work, and why it works and why it doesn't work. Okay, so let's look at the first one. All right, so I'm looking at my function f of x. F of x is 2 plus x minus x squared. So first thing I do is I'm going to prove that f of x is continuous on the given interval from 0 to 2. How can I prove that f of x is continuous? We just kind of figure out what kind of equation it is. That's where all those different equations come in handy. So we know this is a polynomial. So since f of x is a polynomial, it is defined everywhere. Now, I'm a little picky about how you write this because I don't know if you end up taking calculus in college or Cal 2 or something, if that profession's going to be picky or not. So I do a little formal. Some professions are not as picky as this, but technically what you have to do is we know by definition of a polynomial function, polynomial is defined everywhere, which means it's defined from negative infinity from negative infinity. But I don't care about negative infinity in this problem. This problem, I just care about from the closed interval from 0 to 3. So a lot of professors require you to break that down. Therefore, it is continuous on the closed interval from 0 to 3. I can do that because I've taken humongous and we count the small piece. If it's continuous everywhere, it has to be continuous in 0 to 3. I can break it down like that. So that's key. I need that sentence on these because that proves the condition for the intermediate value theorem. I have now proven that I have a continuous function. And we cannot even try the intermediate value theorem until I prove I have a continuous function. All right. Next thing is I need to, on the intermediate value theorem, look at f of a and f of b, and we have to look that we're going to have some f of c in between that. So I need to figure out what f of a value is and f of b value is. So your next step is you need to find the function value at each endpoint of the interval. So I need to figure out function value at 0, and I need to figure out the function values at 3. So that's your next step, is you're going to find f of a and f of b, what they equal to. So if I do that, plugging in 0. So what's f of 0? 2. What's f of 3? Negative what? So we have 5, in my head it's 9. Okay, 9, so that would be 4. Thought I heard 3, I didn't hear it right. Okay, so the next condition, now k was our y value, right? Because that was defined up here. F of c is k. So the next thing you look is k in between these values. Okay. Also, since f of 0 equals 2 and f of 3 equals negative 4 and negative 2 is less than or equal to 1, which is less than or equal to, oh, sorry, you gotta say negative 4 first. Negative 4 is less than or equal to 1, which is less than or equal to 2. The intermediate value theorem applies. We have to use the intermediate value. So I've met the condition. First I have continuous. Then the value, the y value here is between the two given function values, the y values at f of 0 and f of 3, the input values. All right, so therefore, by the intermediate value theorem, there exists x equals c such that f of c equals k. We'll leave this all at s is to 3. Just to make sure. Number of c such that f of c equals k. Yeah, that finished up the 3. So first, let's sketch the graph of our polynomial from 0 to 3. Right. So I'm only going from 0 to 3. I know f of 0 is negative 2. Okay, f of 0 we know is at 2. We know f of 3 is at negative 4. We know this is a quadratic that's face down. It has a y-intercept at 2 that I can look at. That's at an equal to 0. We can solve that equation. And we also know that it goes up a little bit. You can easily get this from your graph. It goes up a little bit and down like this. So that's our f of x graph. Then it said graph y equals k. What was k in this problem? 1. So y equals 1. Oops, I'm a little off. Y equals 1. And see, it works. There's some c value. There's my c. Such that is true. Some c value that gives us a corresponding f of c value. Work out there. Hardest thing about this is the wording. a little picky on the wording. You're using the theorem. Some professors find all the time. So, see if you can kind of figure out this one. F of x is equal to the square root of 25 minus x squared. Oh, that's our first rational function. Where is that square root function defined? Is it continue with that? This continuous everywhere is defined. So how do you figure out when a square root function is defined? What works, what doesn't work? Define our domain of any square root function. No? What can you not do underneath the square root? Negative. So it's where whatever's underneath the square root has to be greater than or equal to 0. So that's what you're going to have to find. So your domain is anywhere, whatever the underneath the square root is greater than or equal to 0 at. You remember how to solve a quadratic inequality? A lot of people forget how to do that. Alright, so we know that this is a rational so since f of x is a radical function, it is continuous everywhere is defined. X is defined. And we got to figure out where it's defined. So we know that this is going to be wherever is underneath that square root has to be greater than or equal to 0. How can I figure that out? I remember how to solve a quadratic inequality. Yes, that's a difference of squares. So yeah, we can do that. Now what do we do? Well, you do set it equal to 0. So, and then we're going to have to look at the number line. So you kind of have to tailor, kind of pause on the inequality and then move over to the equal to problem. And then you do the set it equal to 0. So I got 5 minus x equals 0, 5 plus x equals 0. I get 5 equals x, and I get x equals negative 5. But that's not, I have to figure out that's where it breaks up at. That's where it's equal to 0. So now my function value is 0 at negative 5 and 5. So now I got to figure out when is it positive, when it's negative. So you do test points. So you just pick a number less than negative 5, can be any number, say negative 6, and plug it in here. So if I take 25 minus negative 6 squared, negative 6 squared is 36. 25 minus 36, does that give me a positive or a negative? That gives me a negative. Okay, now I'm going to do the same thing for some number in between negative 5 and 5. Let's try 0. 0 is easy. Plug in 0. 25 minus 0 is 25. So that's positive. All those numbers in that interval will be positive. Choose something greater than 5. 7. Try 7. 7 squared is 49. 25 minus 49, positive or negative? That's negative. Now I want it greater than or equal to 0. So my work was only the ones equal to or greater than 0. So f of x here is defined from negative 5 to 5. That is the domain of this function. And since it's defined from negative 5 to 5, it is also continuous on the closed interval we're talking about, because negative 4.5 is included in that, and 3 is included in that. I can break it down to negative 4.5 equals 3. So I met the continuous requirement. Now I have to check and make sure my endpoint of my interval, the y value of my endpoints of my interval, encapsulate 3. The 3 between the y values of my endpoint. So now we got to figure out what f of negative 4.5 is and what f of 3 is. So what did you get for negative 4.5? So negative 4.5 squared, and then 25 minus that answer. I got 4.75. And
That's minus square.
oh, sorry, I didn't square root. Thank you. I just wrote that as a square root. Yeah, thank you. It is not my day today. Y'all have to really watch me today. Alright, square root of that is 2.18. That'll be close enough. 2.18. Okay, and for the next one, it's just 4. That one's easier. That one's 4. Okay, we need a check. Is 3 between those two values? Yes. All right, so I'll give myself some more room over here. I'll continue writing my answer here. All right, so we know f of negative 4.5 is equal to 2.18, and f of 3 is equal to 4, and 2.18 is less than or equal to 3, which is less than or equal to 4, by the intermediate value theorem. So we got the two requirements, continuous and confounded to the point, by the intermediate value theorem. There is abbreviations to write. Instead of that there exists some C such that f of C equals K. You can use that abbreviation. So it exists, that faculty and for there exists, and S T stands for such that. That's used a lot in phrase. There exists some C such that f of C equals K. End of proof. Okay? Graph of this, I don't know if you know about square root, that perfect square underneath a function like that, but it's going to just be a semicircle. From negative 5 to 5, that's my function value, but I only wanted this from 4.5. Probably something like that, to 3, which is about here. That's my graph of x in the interval that they asked for. And then we know that there exists some C such that K was 3. So at a y value of 3, which would probably be about here. There's my C. Just a quick sketch. All right, only 5 minutes. I guess I'd really love to do this last one, but we'll be okay. We got through. Any questions over the intermediate value? What are the conditions of the intermediate value theorem that has to be met? Has to be continuous, so we first have to show somehow that it's continuous, and what else? to be between those. And sometimes they will give you K. The most common way of using the intermediate value theorem is to prove zeros. So prove a function has a zero in this interval. So basically, if it says, if I ask to prove that this function has a zero in the interval, basically what you have to look at is f of A and f of B. One has to be positive, one has to be negative. The only way I can get to zero as a y, therefore, if we're proving that zero, your y value is zero. So the only way I can get a y value of zero is if I switch from positive to negative. So you'll see it phrased like that quite a bit. So we're giving you the K, and I think I did that on the homework. I asked you to use the intermediate value theorem to prove that the function has a zero on the interval given. And so for that problem, the only difference is K is zero. You have to know that for it to be a zero, you're looking for the y value equals zero. And so everything else is the same. So you'll have one positive endpoint function, y value is positive, one more value is negative. Okay. Any other? Cover the watch today. Any questions on that? We have now finished continuity. And we got the intermediate value theorem, so we're ready for a quiz. Okay. So next, we're going to have homework over this. First part of class, I'll answer questions over homework, and then we'll have a quiz over this concept. So everything since the last quiz is on this quiz on Saturday.